Hello there. I am Joyce Magtibay from BSHM 43B and I will be discussing the center of gravity approach, break-even analysis, and the transportation method. The center of gravity approach. When we used the low distance model, we compared only two location alternatives and the low distance was lower for Springfield than for Mansfield. However, we can also use the model to find other locations that may also give an even lower low distance score than Springfield. An easy way to do this is to start by testing the location at the center of gravity of the target area. The x and y coordinates that give us the center of gravity for a particular area are computed through these formulas. The x coordinate for the center of gravity is computed by taking the x coordinate for each point and multiplying it by its load. These are then summed and divided by the sum of the loads. The same procedure will be used to compute the y coordinate. And here it now goes. The location identified with the center of gravity puts a larger penalty on long distances. This can have practical value given that longer distances impose more cost on the organization. However, the location identified may not be a feasible one because of geographic restrictions. For example, the center of gravity might turn out to be in the middle of a lake. However, the center of gravity provides an excellent starting point. We can use it to test the low distance score of other locations in the area. Break-even analysis. It is a technique used to compute the amount of goods that must be sold just to cover the cost. The break-even point is precisely the quantity of goods a company needs to sell to break even. Whatever is sold above the point will bring a profit. Below that point, that company will incur a loss. We discussed break-even analysis before as a technique for evaluating the success of different products. Now in this chapter, we will use break-even analysis to evaluate different location alternatives. Remember that break-even analysis works with costs such as fixed and variable costs. It can be an excellent technique when the factor under consideration can be expressed in terms of cost. Let's briefly review the break-even equations. Wherein F is the fixed cost, C is the variable cost per unit, Q is the number of units sold, and P is the price per unit. At the break-even point, total cost and total revenue are equal. We can use those equations to solve for Q, or the number of units sold, which is the break-even quantity. Now let's look at the basic steps in using break-even analysis for location selection. Step 1. For each location, determine fixed and variable cost. Step 2. Plot the total cost for each location on one graph. Step 3. Identify ranges of output for which each location has the lowest total cost. And step 4. Solve algebraically for the break-even points over the identified ranges. Take note that the expected demand is to be 10,000 units per year. For this step 1, let's recall. Fixed costs are incurred regardless of how many units are produced and include items such as overhead, taxes, and insurance. Variable costs are costs that vary directly with the number of units produced and include items such as materials and labor. Total cost is the sum of fixed and variable costs. Step 2. To plot any straight line, we need 2 points. One point is Q or unit sold is equals to 0, which is the y-intercept. Another point can be selected randomly, but it is best to use the expected volume of sales in the future. Step 3. Identify ranges of output for which each location has the lowest total cost. And for the step 4, we should just select the location that gives the lowest cost for the range of output required by the new facility. We've already identified the fixed and variable costs. The next step is to plot the total cost of each location on a graph. For each line that we have to plot, we need 2 points. the first point can be units sold is equals to 0. For the second point, we can compute it by using expected demand, which is the units sold is equals to 10,000 units. For the units sold, which is the 10,000 units, we compute the following total cost for each location. You can see that depending on the range of output, locations C, B, and A are the best ones. Location D is never a best option. We can see the approximate ranges for each location here. We can compute the exact ranges for each location by finding the exact output level for which locations C and B are equal and locations B and A are also equal. We can do this by computing the output levels at which the total cost equations for these locations are equal. Thus, the point between C and B is 4,666.7 or roughly 4,667 units. In here, the breaking point between B and A is 9,000 units, which means that location A would provide the lowest cost if we produce 9,000 units or more. If you plan to meet a demand of 10,000 units, we should select location A. This problem can also be solved using a spreadsheet as shown on the next pages. The transportation method. It is a linear programming that is a useful technique for solving specific location problems. It is discussed in detail in the supplement for this text. The method relies on a specific algorithm to evaluate the cost impact of adding potential location sites to the network of existing facilities. For example, an existing network of facilities may consist of multiple sending and receiving sites. Our task may be to evaluate adding a new location site to this network, either a receiving site or a sending site. We might also wish to evaluate the adding multiple new sites or completely redesigning the network. The transportation method can efficiently analyze all these situations and provide the lowest cost for each configuration considered.